Hi everyone, and welcome to this Lloyd's Lab Spotlight Series event on the impacts of quantum computing on insurance, where I'll be exploring both the opportunities and the threats, in particular the cyber threats to encryption posed by this emerging technology to the insurance industry. So what is quantum computing? The image you can see on the right hand of the screen is an image of a quantum computer. And as you probably noticed, it looks absolutely nothing like the laptop device that you're viewing this webinar through. And that is because quantum computing is a fundamentally different type of computing technology. It's based on the laws of quantum mechanics, which are the laws of nature that govern really tiny objects and can lead to all sorts of weird and wacky phenomena. And it can perform calculations that are not currently accessible to the computers we have today. So it's important to stress that quantum computing isn't just a more powerful version of classical computing, but it's an entirely different technology paradigm that can be used to solve problems we have no other way of solving with the computers we have today. In the words of Richard Feynman, I think I can safely say that no one really understands quantum mechanics. And so I'm not going to try and give you a physics lecture, but I do briefly want to touch upon how quantum computing is different. So in classical computing, information is represented by bits, which can take really well-defined values of either 1 or 0. So all of the images, emails, and even this video coming to you is represented by a string of 1s and 0s in a computer. However, in quantum computing, information is represented by qubits or quantum bits. And the difference is that qubits can have values of 1 and 0 at the same time, or any of the infinite combinations of the two. Qubits can also interact with each other via quantum mechanics. And all of these properties, plus a lot more, means that quantum computing can perform calculations in fundamentally different ways. And in some instances, this can give quantum computing an exponential speed up in solving certain type of problems. So why don't we have quantum computers yet, despite the enormous amount of development made in this field, particularly in recent years? Well, that's because there still remains some really complex hardware challenges. For example, the qubits that we spoke about, it's really difficult to keep them in the quantum mechanical state that they need to be to perform calculations. And with some qubit technologies, we even need to cool them down to temperatures below that of interstellar space. However, there's also been increasing investment globally, both in public and private sectors in this new technology. Firms received $450 million in 2017 and 2018, which was a $300 million increase from the previous 2 years. There's also been $22 billion in public national initiatives worldwide, with China taking the lead. We've also reached some really exciting milestones with this technology. For example, Google reached quantum supremacy in 2019, and just a few months ago, in December 2020, a group of Chinese scientists reported quantum advantage. And both of these terms mean that for the first time, it was shown that a quantum computer could solve a problem faster than a classical computer. Amongst them, quantum computing hardware players are the major tech companies. And there's also been a host of quantum computing software and service companies that have emerged in recent years. And this is really surprising given the fact that they are building software for hardware that doesn't even exist yet. But this just goes to show the confidence that exists in the emergence of this technology and how important it's going to be. And there are a lot of companies that are already trying to see what problems that they have that quantum computers can solve, and they're partnering up with these software and service companies to be able to find solutions to those. So I want to give you a few examples of the cool kind of things quantum computers can actually do. They might be able to help with drug discovery and design. For example, quantum computers might be able to simulate molecules and enzymes and proteins, something that we currently can't do with our classical computers. And this can drastically shorten the life cycle and cost of drug development, which on average takes currently 10 to 15 years. They can also be used to tackle climate change. And what I mean by that is that quantum computing can be used to address some of the most carbon-intensive processes we have by streamlining a lot of these processes. So 3 broad categories of problems that quantum computing is best suited to are optimization, simulation, and machine learning problems. And it's important to note here that quantum computers are unlikely to replace our laptops and smartphones, but they're more likely to be involved in a hybrid solution for solving particular problems. So bringing it a little bit closer to home, I want to speak about a few of the operational benefits that quantum computing can offer to insurers. For example, the ability to process large amounts of data might mean that they can help us gain a greater understanding of risk and improving pricing risk models. Quantum computing might be able to accurately simulate weather systems one day, which obviously has huge impacts on the insurance industry. It also allows the modeling of aggregate risks, which is something that's really hard to do with the computers we have today, just because of the number of variables involved in these problems. And so that can, for example, help with modeling of supply chain interruption, liability risks, or cyber risks. It will also, in general, improve machine learning capabilities, which in the insurance sector can help us with improved customer relationship management, fraud detection, and even better predictive analytics.